Today's topic is third law of thermodynamics. This topic has become the part of your past papers many times, so it is highly important topic to be learned. So according to Nernst heat theorem, the value of delta Cp mean molar heat capacity is 0 at the absolute zero temperature. You have studied it in the Nernst heat theorem in the detail that at the absolute zero value the molar heat capacity is becoming zero. It means that when we apply this condition, the capacity of the reactant and product must be identical. So when we apply and when we talk about the quantum theory of light, it comes to know that when we talk about the capacity, molar heat capacity of the solid at the absolute temperature 0, it is 0. Further, the Nernst heat theory also helps us to determine that the solid component means the components that are having well arranged molecules and well arranged atoms in them, and there is not the space for the molecule or the atoms to move around. So the randomness of the system or entropy of the system is also 0 at the 0 Kelvin. So by applying the condition here, we are saying that the limiting factor is that temperature is coming towards the 0, approaches to 0. At that time, entropy of the solid state will be exactly equal to 0. M. Planck took this idea one step further, and what does it state? It stated that every substance has a finite positive entropy, but at 0 Kelvin the entropy may become 0. As the temperature decreases, the entropy decreases. So when the temperature becomes 0, the entropy also becomes 0, and this is perfectly applicable on the crystalline substance. The entropy of pure element or substance is in a perfect crystalline form is 0 at absolute 0. What does that mean? Means that the entropy of a pure element or a substance is 0 when that substance is in perfect crystalline form at absolute 0 temperature. The statement gives us let us to know that this application is only confined to the pure crystalline form, because when we say that at absolute temperature 0 the entropy is 0, this is not observed in the case of the solution in the liquid form and the supercooled liquid solutions, because supercooled liquid solutions mean frozen solutions, frozen liquids, and the solution form are showing somehow the species randomness or the availability of the chances for molecules or atom to move around. So this is the reason that even in this frozen form the liquids are supercooled liquids are having not zero entropy. So it means that this rule where we are stating that at absolute 0 temperature the entropy is coming 0 is only applicable for the crystalline form. Perfectly crystalline form means that the pure substance that exists in its crystalline form have the 0 entropy at 0 Kelvin temperature. Another fact to be determined here is that it is impossible by any procedure, no matter how idealized, to reduce the temperature of any system to absolute 0 in a finite number of operations. Means that when we are taking through a procedure, when we are observing a reaction, no matter how idealized situations are given, how idealized conditions are given in a reaction, in a mechanism, in a system, it is impossible to get exactly absolute 0 temperature in the finite number of operations. Means that limited number, how many we do doesn't matter, 3 4 7, these are always finite. This cannot be infinite, because the number of experiments always stay finite. Even we go to the 1000 times 1 to for the one operation, so it remains the finite. So we can say that in the finite number of operations it is impossible for a system to attain the absolute 0 temperature. It means that it is impossible for a system to have absolute 0 entropy, because absolute temperature is not achievable in the finite number of operations. So means that the law where we say that at absolute temperature the entropy is becoming 0, that is also not applicable and reachable. Means that whenever we talk about the solution or the supercooled liquid, there is somehow a capability chances or probability for the small randomness. When apply the limiting factor T approaches to 0, the entropy is equal to 0 for only perfect crystalline solid, not about the solution of liquid form, not about the frozen liquid, only perfect crystalline solid, not even for the amorphous solid, only for crystalline solids, where the molecules are highly well arranged, are highly organized, having particular angles with each other. There is no capacity for the molecules to leave their place and to have the disorderness, otherwise the structure will be deformed and the crystalline structure will lose its identity, and in fact the molecule will be changed. So that is why in the crystalline form, in the perfect crystalline form, solid have only the zero entropy at the absolute zero temperature. The value of molar heat capacity at the constant temperature, pressure decreases with the pressure in temperature and ultimately becomes zero when the absolute temperature reaches to zero. We have studied it, and this is also about the third law of thermodynamics, where it is saying that the molar heat capacity is equal to the change in the heat with respect to the change in the temperature at the constant pressure. So in the second law we have studied that the entropy is equal to the del Q over T, means that the change in the heat coming from the source of temperature. So when if we want to take out the value of the heat change, delta Q is equal to the TdS. By putting the value of the delta Q or the change in the heat in this equation, the equation become in this way. If we rearrange it to take out the value of the entropy change, the equation become in this way. And if we take the integration on the both side by applying the limit, where we are saying that the limit of for the temperature is that when the temperature was zero, when the temperature is somehow available, and the entropy is that when the temperature entropy at the absolute zero, entropy when the temperature is somehow available. Okay, when we open up the applied limits, then it shows that entropy at some temperature minus entropy at zero. You know that when the temperature approaches to zero, absolute zero, the entropy also becomes zero or decreased to minimum number. So it means that it is a smaller value than the st, so that's why we are subtracting it. And the other side is in the same way. According to this equation, shows that the value cp must be absolute zero, means that they are talking about, this is all about the situation when this is equal to the zero situation, zero temperature. And the third law can be stated like this: when the cp, when we have talked about the entropy now, where we said this limiting factor is that temperature approaches to zero, at that time s is equal to zero for pure crystalline form. Here we are proposing that, and here we have mathematically derived that the limiting factor is temperature approaches to zero. At that time the molar heat capacity must be is equal to zero, and obviously it is also for the particular substance. That was all about the today's topic. I want to make you know that today we have talked about the third law of thermodynamics, that stated the previous, that also accomplish and also certified the previous laws, that it said that at the absolute zero the entropy is zero, molar heat capacity is zero, but it has added some value in the previous law, where it is stating that it is impossible for a finite number of operations to gain the absolute zero temperature, and then it is impossible to gain absolute zero entropy for the substances that I have told you about, the solution form and the frozen liquid solution or the super cooled solution, right? And only thing that is possible for the absolute temperature zero and the zero entropy is for the crystalline form. And the same goes with the molar heat capacity. Molar heat capacity is zero at the absolute temperature, it decreases with decrease in temperature, and at the end we are saying that when the limiting factors are applied, the molar heat capacity of our system must be zero of a solid substance. That was all about the third law of thermodynamics.